Hey guys, welcome to one more session of my architecture and technology series. Today we'll talk about compilers and interpreter driven languages, right? And I'll also tell you why it's not so much about being black and white, right? This is interpreter driven, this is compiler driven, and so on and so forth. Like what it used to be like a decade and a half back, but it's more like a continuum where it's very hard for you to see or say that this is basically a compiled language while this is an interpreter driven language. Okay, but before that, one of the things I'd like to say is that if you go to Tech Empower, which is a benchmark site, right? Tech Empower gives you benchmarks or performance benchmarks for a wide variety of programming languages on various environments, right? So whether it's Java, JavaScript, Python, Rust, Golang, C, C++, in various flavors of operating systems with various databases, with MySQL, MongoDB, all these permutations, combinations for something that is not that is non-trivial. For example, the standard benchmark they have is there's an inquiry that happens, and then you kind of filter it. There is a set of records, and then based on this, certain additional records are being read from the database. Those are merged together, and a result set is returned. So it kind of tests an overall performance. It's small enough to be easy to develop. Plus, it is also fairly non-trivial enough to have a actual real life representation, right? Here, if you look at this benchmark, you will find that a Node.js Express framework outperforms a Java Spring-driven framework. All right, in terms of how many requests it can handle on a per second basis. Right? How does this happen? Because I'm sure as an upcoming techie, you will understand that Java is compiled, whereas JavaScript is interpreter-driven and so on. All right. So to provide a good perspective and a good understanding for you, right, as an upcoming techie, we'll take a few languages and then we'll try to understand what does it mean, what actually happens. Is it interpreter driven, is it compiler driven, so on, right? So what is an interpreter driven language and what is a compiled language in the traditional sense as it was understood before, right? When you say interpreter driven languages like Python or Perl, what is generally understood is that you write the code, so it's served as a .pl file or a .py file or a .js file or whatever, and then there's a program that kind of runs it, right? So for example, the Python application, I might say Python and provide the program name. So Python is basically the interpreter. It reads this file and then it executes this series of instructions that is given in this file. So that's essentially an interpreter. Whereas you look at C or C++, what happens? We write a program in a .c file or a .cc file or in a .cpp file, depending on what kind of operating system you use. And then you compile it. There's a compiler chain that happens. And of course, there is a preprocessor involved and so on and so forth. The compiler chain itself is fairly complex and there are a lot of parts in a compiler chain. But at a high level, there's a compilation phase which takes the source code and compiles it and produces an output which is a binary format or a binary executable. Okay, so on Windows it might be a .exe file. On Unix systems it might be an ELF binary which is directly executable, which means when the program ultimately executes, you don't need a C++ interpreter or a compile anything else. So as a compilation phase, produces a binary, then it runs, right? Java is maybe one of the first systems that actually kind of bridge this two together, right? By providing what was called a just-in-time compilation. So when you compile Java, what happens is it doesn't compile directly to machine code, at least when it originally came on, right? What used to happen, it would produce a .class file, which is an intermediate format, all right, which is called Java bytecode. This bytecode is then executed by the Java runtime, and then execution happens. All right, so initially it used to be like an interpreter of the bytecode, and then what happened was that they provided something called a just-in-time compiler, right? What the just-in-time compiler used to do is it used to take this bytecode and then at runtime it will compile it into the particular machine language code, right? Depending on which particular architecture is running on. Architecture in the sense if it runs on a series on i386 or it runs on some other processor or name whatever, right? So depending on it, it will compile it and then it will run it. And then the Java ecosystem evolved into what was called hotspot compiler, where see interpreter from an interpreter to making a compiled application, there's a lot of processing involved, right? Supposing there is a piece of code that is executed only once, what is the point of compiling it? It's just a waste of time, right? During runtime itself, there's so much overhead required when you actually compile it. And when some piece of code is executed once or twice in a day, there's no point in actually compiling it. It can as well be interpreted. That way, we save a lot of time. So that's how this concept of hotspot came in. So hotspot, what it does is it identifies portions of your code, a portion of the byte code, which are executed many, many times, and then those hot spots, right, so to speak, get compiled to machine code. So even though Java compiler produces only bytecode, ultimately what will happen in most of the cases which are executed many times is that what is actually executed is machine code, right? So here again, the difference between what is an interpreter language, what is a compiler language, kind of fuzzes out, and hence we call Java a compile language in many ways, because you basically compile it to bytecode and then that gets executed. All right. Now let's look at JavaScript, which is very interesting, right? Now, if you look at the V8 engine for JavaScript, there's been a lot of improvements in the way the entire thing executes. All right. Now, one of the biggest advantages of having an interpreter is that it's ultra fast, instantaneous. I have source code, there is no compilation step. I fire it, it runs. Just like that, right? Okay, on the other side, what is the advantage of compiler? Obviously, speed, right? When it's running as native machine code, optimized machine code, obviously the performance is going to be leaps and bounds much better than anything that's interpreted, correct? So when it comes to JavaScript and V8 engine, what the engineers essentially have done is to provide you with three stages. All right. And because V8 is basically a term that's borrowed from the automobile industry, these other terms also are borrowed from the auto industry. So they have something called as ignition, they have something called as a spark plug, and then they have something called as turbofan. All right. What ignition does is it takes your JavaScript files, it basically does all the checks, and at runtime quickly converts it into an abstract syntax tree, which is pretty much like bytecode. All right. Except that there is no compilation step that is separate. It's not like that you have a compilation step where you go from the JavaScript source file into JavaScript bytecode. That doesn't happen. It happens on the fly. The moment I execute something, so the ignition takes up, it does the AST and then starts executing, right? From there, on the other side, you have turbofan. Turbofan takes a bit of time. Basically, it takes your AST or the abstract syntax or the bytecode, if you want to understand it that way, and then it compiles it into a highly optimized machine code. Optimization could be many, right? Compilers will do. They might aggressively go in inline code. Inline code means, for example, if I have a function call, instead of having those function calls where the variables are stored in a stack register, then the call is made, then they are popped off the stack and all that. Inline will basically take all that code and just plug it in. It's so those kind of optimizations typically compilers will do. So that's turbofan. In between, they have something called as spark plug. What spark plug does is it is a compiler, but a non-optimizing compiler, meaning it takes abstract syntax tree, ignition gives, and then it directly compiles it almost one on one into machine code and executes it. So when you actually execute JavaScript, right, even though your understanding might be different, saying that it's interpreter driven, what is actually executed 80%, 90% of the code that is actually executed many times is nothing but pure machine code. Exactly the way C or C++ essentially, you are going to execute, right? And essentially the way the hotspot compiler in Java is going to do. Which is why Node.js today is, on a performance perspective, on par or even better than Java. And one of the reasons why it's better is because Node.js, in addition to V8, also adds libuv to it. Okay, let's look at what it is, right? Now, when I make a function call, or when I try to read a file through my JavaScript application, which is executed by V8 engine. So in V8, I supply a JavaScript file, the interpreter, right, which is ignition starts off, it produces an abstract syntax tree. Then from there, Sparkplugs takes over, does a quick optimization compilation step, and then the hotspot logic kicks in. It sees what is the code that is being executed many times, then it uses turbofan to make a highly optimized machine code, and that is what is being executed. All right. In addition to this, there are a lot of file system calls that are going to happen, right? When you want to read a file, there's no point in waiting, correct? Because IO is always significantly time consuming when compared to what is being executed inside your register, right, into the CPU. So libuv is a library written in C++, very efficient library. There is one library version for each operating system and each system architecture, but the interface it provides on top is the same. All right, it's almost like an API, a system level API. Underneath, the internals are different. All right, this takes care of file reading, file output, socket output, communication, HTTP communication, a whole host of IO. So the moment you inside your Node.js application, for example, if I try to read a file, that particular thing is optimized already in machine code. Your code is already running as an optimized machine code over here. Now it calls libuv. Libuv will immediately make it asynchronous, so it doesn't wait. So your code goes and executes the rest of the things. Libuv does all its processing, and then the callback function which you position somewhere is then called by libuv after the results are over, which is why this combination of highly optimized compilation, which is running an optimized version of your machine code, plus the entire reactive architecture is what makes Node.js so very compelling from a server-side development perspective. In addition to, of course, the productivity of JavaScript itself, in that uh, anything that you can write in Java in terms of performance, the same kind of performance a good Node.js developer can always achieve that kind of performance or even better performance in Node.js, right? So that's essentially what it's all about today. So, like instead of what it was like a decade and a half back, where there were interpreter-driven systems and compile systems, what is today, if you look at the compiler chain today, it's kind of the best of breeds, right? So it takes the best of both worlds, the fast startup times of an interpreter compiled with the fast execution times of a compiler, kind of marries everything together and gives you a fantastic piece of technology that's both very productive to develop and also blazes away from an execution speed perspective. Thanks for watching. Hope it was